Okay, 15.5 or 6, depending on the school you're attending. Cal Poly, this is 15.5. Pasadena, this is 15.6. Triple integrals and rectangular coordinates. So, just like we did the double integrals, if we look at this rectangular box, first we start with rectangular box. If I break this, into a bunch of rectangles, n of those, m of those, and so on and so forth, what I'll get a bunch of those. Oh, you really killed it. I can do a better job than that. So if I take one of those, let's say in the middle, there. If I take one of those, I'm looking pretty much at so this right here is the change in y, this right here is the change of x, and this right here is the change of z. So if I really call this the volume of if I call this f of x sub I j k, y sub I j k, and z, okay, make a big mess out of this. So if I call this f of x sub I j k star, y sub I j k star, and z sub I j k star, and if I take the series I equal 1 to L, j equal 1 to m, and k equal 1 to n of f of x sub I j k star, y sub I j k star, z sub I j k star, pretty much dv. That is, the I star I j k of x, y, and z don't have to be specifically in the middle or on the right or on the left, kind of like you could pick those at random, identical to what we did before. And if we take the limit, as L, M, and N approach infinity of this big mess, what would we get would be the triple integral over region B of f of x, y, z dv. And that's pretty much how things work. I could have derived that and spent time on it, but I just want to spend more time on the homework. There's really not much difference between single, double, and triple integrals. So if I wanted to talk about a volume, if the volume over a closed bounded region D, that must be the case, in space is given by the volume equal again. If you put a 1 right there, you get the volume. Just like if we had a double integral and we put a 1 there, we get the area. And if we had a single integral, it's kind of like talking about length. So not much difference between a double integral and a triple integral, except that's really how things should work. So we start off with an example. Here's one. And don't worry if you're worried about what does this look like. We're going to graph all of those soon, and we're going to worry about how to do this, vertically, horizontally, you name it. We're going to do every possible scenario you could think of. For now, do you know how to integrate this? Well, if the last outside most integrals are numbers, that's always what you want. Well, isn't this, with respect to z, isn't that 3x times z evaluated from 0 for x plus 2y? Plug that in for z. Again, as far as z is concerned, that's a constant. That's x plus 2y minus 0. So I'm looking at 3x squared plus 6xy. Take this now and let's integrate it with respect to x. So I'm looking at the integral from 3y to y squared of 3x squared plus 6xy dx. As far as x is concerned, that's x cubed plus 3x squared y. Evaluate from x equal to 3y to y squared. That's going to be y to the 6 plus y squared 3y to the 4th minus 27y cubed minus 3 times 3 is a 9 for x. Nope, I messed up. So if you put the 3y in there, that's 9 times 3, 27. Y squared times y is y cubed. Oh, that cancelled out. What a nice coincidence. Now what? Now I go for the last outside integral with respect to y of y to the 6 plus 3y to the 4th, 0 to 3. That is y cubed over 3 plus 3y to the 5th over 5 evaluated from 0 to 3. 27 over 3 is 9 plus 3/5 times 3 to the 5th, whatever that is. So pretty much integration, a bit tense, it's kind of long. It looks intimidating, not really. Now consider the solid. I'm looking at this, and this is running from U1 to U2. So when I really want to talk about finding the volume of this, and let's say this is over B. If I take the triple integral of this over region B of f of x, y, z dv. Well, the way it works, I will say, if you look over this region D, I have a couple of options. I could say this is the double integral over region D, which is the shadow on the floor. Remember, that is x, that is y. And do keep in mind that if I do that, I would integrate, and this is going to be a key. I'm looking at this from the top. Do you see where you start tracing? From U1, it's important to start getting that. You have xy. And do you see where you terminate? The U2 of xy of what? F of xyz doesn't change. We didn't change that. But instead of dv, since I split it this way, I'm saying you're going to do this with respect to z. And now what? Where this is the area of that region. I don't like that z. So this is going to be a key for what's to come. And now, if you really think about it, I can do this two different ways. You know what? Let me put this up there just so that spacing is very maximized. But I could say that that is the integral u1 of xy, u2 of xy, f of x, y, z, dz, right? I know from the previous section I could write this two different ways. I could say, well, look, what I'm gonna do, I'm gonna run the x and have x run from A to B, and that means y runs from, and you have to do this on a few problems, y run from, if I look at the bottom part, that's really y equal, call it h1 of x, and exits out of the top, which is h2 of x. Or I could have done this and said, wait a minute, no, let's go this way. Let's run y equals c to d, and in that case x would run g1 of y and exits out of g2 of y. So you have that option. What does that mean? That means I could write this 6 different ways. 2 ways if I'm looking at this from the top down. 2 ways if I'm looking at it from the negative x to the positive x, and 2 ways if I'm looking at that from the negative y to the positive y. Now you have to do that on a couple of problems. Most problems you do them the way you see fit, the easiest way out, but theoretically you could do this 6 different ways. So let's start looking at some problems. And here's our first example. Evaluate, this is not volume because they gave us some kind of a function in there. So that's a bit more than we like. What is that right there? You don't have to graph the region, but you have to visualize it to figure out how to set the integral. Now, if I'm glancing at this, this talks about a sphere. Spheres something like this. Okay, now let me see if I could fit that in it. That would be awesome. Sometimes you can, and sometimes you have to adjust it, and it just doesn't match. Okay, close enough. So this is 5. And z equal 3. I have a good idea of what they're talking about. So what are they saying? The bottom half or the top half? What is it that they want? It says, evaluate the triple integral. Now I'm going to set them up, assuming you could integrate, where E is the solid enclosed below, we're enclosed below by the sphere, and above z equal 3. Okay, so below by the sphere, okay, and above by z equal, you know what? That's not, here we go. Below the sphere and above z equal 1. That's better. So how does that look like? If I'm looking at this, and we're saying below by a sphere, now why is it important to get that out of the way? Because since everything is in terms of z, I'm going to run the x plus y makes no difference. If I run this from z, I need to know which region they're talking about. But enclosed below the sphere, there's the sphere, below it and above z equal 3, they're talking about this region. If I think of, in terms of z, running a laser beam where does that laser beam penetrate? Doesn't that hit z equal 3 first? And doesn't it exit out of what? The top? What would the top be? Isn't the top z equal the square root of 25 minus x squared minus y squared? If that's the case, I eliminated the 3D, and now I'm looking at this problem from the top. If I'm looking at this from the top, assume I'm far enough. I don't see the 3D. The only thing I'm gonna see would be that outer rim right there, and it's gonna be a solid because it's the top of a dome. But if you're high enough in space, you can't see the 3D, you only see the flat surrounding of it. Now, how are you going to work this out? Well, I need to know what that radius is. And to get the radius, well, plug z equal 3 in there. That was in your first test. X squared plus y squared plus 9 equals 25. X squared plus y squared equals 16. That's a circle of a radius 4. Wouldn't you be best off, again, once you get the z out of the way, wouldn't you be best off by saying rd theta? Let theta run from 0 to 2 pi, and r run from 0 to 4. Now that you learned about polar coordinates, shouldn't we use them whenever that chance comes up? So there it is. Let me set up another problem. I'll wrap this up in the next video.